let's look at our dot products. Again, the idea is going to transfer from 2D to 3D quite nicely, because a line segment is a line segment. Whether it's in 2 dimensions or 3 dimensions doesn't matter. It's just something that's joining 2 points. So all these properties will remain the same. And if I'm just talking about a vector, or a vector in notation there is like dimensionless. I could be talking about a 2-dimensional vector, I could be talking about 3, I could be talking about 4, 5, 6, 7, who knows? But what we do know about vectors is this. If neither vector is 0, then we know this is our dot product. So u dot v, magnitude of u, times magnitude of v, cosine of the angle between the 2 intervals, or vectors. Now theta could of course be acute or obtuse depending on how we're looking at it. But if one of them is 0, then the dot product will be 0. Makes sense. You multiply by 0, you get 0. So if I write them as column vectors, and now I am talking about 3 dimensions, then we know the dot product will be this. Very similar to the 2-dimensional one, but now we multiply the z coordinates together as well. A reminder of our dot product properties. Well, it's always going to go in between minus the magnitudes multiplied together, positive the magnitudes multiplied together, and that's of course because of the formula is times cos theta, and cos theta goes between -1 and 1. The order that we put them doesn't matter, so u dot v is the same as v dot u. U dot u, that was a very useful one, it ended up being the magnitude squared. This was our distributive law. In algebra we would call it that. Well, it's the same, but remember we're not actually multiplying, it's the dot product. So when we expand this out, it's a dot u plus a dot v. Again, this one, it looks like the difference of 2 squares, but it actually ends up being the magnitude squared minus the magnitude squared, because we get u dot u minus v dot v. The scalar, well, a scalar can just be multiplied out later. It's still just do u dot v, and it'll be multiplied by whatever that scalar is. Now, if u dot v equals 0, then we know u is perpendicular to v. That's still true. U dot v, if it's equal to plus or minus the magnitude of u times magnitude of v, well then that would imply that the vectors are parallel. It's an if and only if situation, an equivalence one you'll notice, because the other way is true as well. If you know the vectors are parallel, then you know that u dot v must be equal to magnitudes. The way I've written this looks strange, because of course how could the absolute value be negative? What I'm getting at is in number 8, if it is the positive number, then we know u and v are going in the same direction. But if it is the negative number when you do your dot product, then you know you're going in opposite directions with the vectors. Well, let's actually prove that property. I mean, we know it's true in 2 dimensions, but will it be true in 3 dimensions as well? I guess that's what I'm trying to prove here. So if I was to expand out, well, let's break it into its components, because I'm trying to prove it's true for 3 dimensions. So the I component, the j component, and the k component. So if I find the dot product, I'll get a1 times b1 plus c1, a2 times b2 plus c2, a3 times b3 plus c2. These are now all just numbers, so we can expand it out, and this is what we get. I now need to be able to regroup this and hopefully come up with a dot b plus a dot c. So if I regroup it, a1 b1 plus a2 b2 plus a3 b3, yep, that would be a dot b, and the second one in a similar way, yep, that is a dot c. So yes, that property does hold in 3 dimensions as well as 2 dimensions, and in fact it holds in every dimension. Let's prove these are perpendicular. A very similar question to what we saw in 2 dimensions. We do exactly the same thing. Let's find the dot product, and yep, turns out to be 0. Therefore, those vectors are indeed perpendicular. Let's look at this one. The point A, so it's there in space. It's got a position vector of A, B, C. The actual vector makes angles with the different axes, so alpha, beta, and gamma with the x, y, and z axes respectively. Now, before I go and show you what this question is, I want to show you something here. If it was 2 dimensions, okay? If it was 2 dimensions, here's the vector. And the vector would make angles with both axes. Let's call them alpha and beta. Now, cos squared alpha plus cos squared beta, would end up equaling? Well, beta is 90 minus alpha. Therefore, it would be the same as cos squared alpha plus sine squared alpha, which is 1, we know. So cos squared alpha plus cos squared beta will actually equal 1. So the angles with the axes. That brings us to this question now, because we're going to prove that's true in 3 dimensions. That the angle it makes with each of those axes, if we go cos squared plus cos squared plus cos squared, it should be 1. I'll let the vector be, well, I'm not going to let it be, they told me it is, so I don't really have a choice. I'm just calling it u. So A in the I direction, B in the J direction, C in the K direction. So u dot I, the angle it makes with the x-axis, if you like, because it's the unit vector in that direction, would simply be A. But also, I know that u dot I will be magnitude of u times the magnitude of I times the cosine of alpha. Well, magnitude of I is of course 1, it's the unit vector. The magnitude of u will be the square root of a squared plus b squared plus c squared. So we end up with the square root of a squared plus b squared plus c squared cos alpha. So we know A is equal to this expression here. Cos squared alpha, therefore, if we play around with this, ends up being a squared on a squared plus b squared plus c squared. I say, I could have done that with the other ones. It's just letters I'm playing with. So cos squared beta will be b squared on a squared plus b squared plus c squared. Cos squared gamma would be c squared on a squared plus b squared plus c squared. So if I add them all together, well, I get a squared plus b squared plus c squared over a squared plus b squared plus c squared, which is of course 1.